So far, we have been using those linear gap penalties. So we are treating those gaps the same way, the way we treated our first gap. But in nature, it has been seen that if there are some indels, if there are some deletions on one side or insertions on other sides, they are more than one nucleotide or one amino acid residue. So if we penalize those alignments the same way, we will end up with low scores. So in order to incorporate the possibility of the longer gaps, there was another these gap penalty scoring scheme have been added. We call them as affine gaps. So we can have an affine gap cost as given by this function. So we have gamma g, which is the penalty for that gap. So that is minus d. So once we start the gap, so there is an gap open penalty minus g minus 1. So g is actually the length of that gap, and d in this equation is the gap open penalty, and e is the extension penalty. So we have g minus 1 into e in this example. So for first gap, we will have the big penalty. But if the gap continues, as in this example we see it as extension penalty. So extension penalties are taken as less penalties. Whereas in comparison to the previous situation, over there we have gamma g is simply the product of d with g. So length of the gap simply multiplies with the penalty. We can now take this situation and make a diagram. We call, in computational language, we call it as finite state automata. So where we have different states and systems, they move from one state to another. You might have seen that in your computer courses. So here actually I captured this figure from Durbin's book. So over there what they have done is they have tried to represent this situation with the help of this finite state automata diagram. So what we see here is we can have these three states. We can break our system in three states. So first is where we have a match state. We have actually elements on both sides, on one strand as well as on the other strand. So we'll have this situation. Remember guys, mismatch is also part of this same state. So we have match or mismatch fitting over here. So the system keeps on operating as long as we get those two elements coming on both sides, and we are either putting them in the shape of a match or mismatch, but we simply are placing them together. So in that case, it keeps on operating over here, and score goes like this. So sometimes we get insertion on, say for example, x is our top strand and y is our bottom strand. So here we can observe insertion on x. So we can have some symbol on x, but we have a gap on y. So in that case, from this match state with the penalty minus d, which is the linear gap penalty, system moves to this situation where we have ix, insertion over x, and a gap over y. So it keeps on operating over here with e, which is the gap extension penalties. As soon as we get symbols in both of them, after having, say, these three gaps, here we have this linear penalty and here we have this extension or affine penalty, we reach here something like. So we reach a situation where we have symbol over here, symbol over here. So again the system moves back in this direction. Same way, we can have another situation where we can have insertion on y. So where we have elements present on the second strand, so that is iy state. So here again minus d, and if it keeps staying over here, there will be the penalty like this, and it can go back to this situation. So in this way we can model our system with the help of this diagram and recognize three important states in our system, and those drivers of these states are these scoring systems like these, where situation where we get the match or a mismatch, or situation where we get this gaps starting or gap continuing, coupled by their respective penalties. So if we put this situation in the model, it becomes little more ugly. So over here we need to put in our scoring scheme these two states also, and we are again picking a situation where we have this situation and in case of the gaps we have this one and this one. So this makes our this algorithm really complicated. I don't want you to go into details of it, but just try to understand that it exists over there. So here we have this match state, here we have insertion over X, here we have insertion over Y. Same way the matrix becomes ugly, so it looks something like this. So in those traceback pointers are on here, I'm just looking or zooming in into a part of it. So over here we'll try to pick up where we get the maximum score in any of those states. So for example, if we compare all these cells, we see that here match is the best explanation, so match and the score is 1. Here the score is 2 as compared to rest of them. So we start picking up our maximum scores wherever we have. So max, these are low by the way. So here we are kind of incorporating and affine gap penalties, but this is how it looks like. This dynamic programming approach becomes more complicated. So in this section we just try to look into that there are some additional gap penalties. We call them as affine gap penalties, where we have extensions, or the gap extensions are treated differently than gap openings.